To all my viewers, feel most welcome into our today's discussion whereby we are going to discuss about the inverse Laplace transform. When it comes to the inverse Laplace transform, we understand that it involves working from the answer back to the equation. And we know that it is denoted by, this is the sign of the inverse Laplace transform, well, this is the sign of the Laplace transform. But we understand that it does not involve getting the reciprocal. That is the main key point that you need to understand. In my previous videos, we've learned that the Laplace transform of our function f of t was converted from the time domain into the frequency domain, which was given in algebraic function. But here now we are going to work from the frequency domain, which was given in the algebraic form, back to the time domain, which is equals to our function f of t. All these working involve carrying out partial fractions. When it comes to the partial fraction, we understand that the numerator must be of a lower degree than the denominator. This is our example here. When we check here, we are having x squared, we add to x, we add to 3. Here it is 2x squared. All over x we subtract from 1. But the rule says that in the partial fraction, the numerator, which is whatever we are having here, must be of a lower degree than the denominator. To mean that you must do your partial fraction correctly so that you can reduce the numerator into the first degree as whatever we are having on the denominator. Let us now get into our Roman 2, factorize the denominator into its prime factor. And this is what we are going to follow. These are the rules that we are going to follow in factorizing the denominators into their prime factors. Number 1, linear factor. This is our denominator. This one we are going to denote it as a all over s we add or subtract from a when we are having a denominator like this one. How about now the repeated factor? The repeated factor, here we are going to have a all over s we add or subtract a, we come and add to b all over s we add or subtract a, but here now we are going to have it square. How about when now it is to a power of 4? When it is to a power of 4, we are going to have a all over s we add or subtract a, we come and add to b all over s we add or subtract a, this one is going to be squared, we come and add to c all over s we add or subtract a to a power of 3. When it comes to d, we are going to have s we add or subtract a to a power of 4, because here it is to a power of 4. Let us now discuss about the quadratic factor. When we've been given a quadratic factor on the denominator, when you've been given a quadratic factor of, let's say, s squared, we come and add to ps, we come and add to, it can either be a positive or a negative. Here we are having q. This is what you've been given on the denominator. Here we are going to have as we add to b all over s squared, we add or subtract to ps, we add or subtract to q. This is what we are going to have. Or in some instance you can be given s squared, we add or subtract to ps, we add or subtract to q. But here Everything has been raised to a power of 3. Here now we are going to have as we add to b all over s squared, we add or subtract ps, we add or subtract q, we come and add to cs, we add or subtract to d all over s squared, we add or subtract ps, we add or subtract q. Here we are going to have squared. We come and lastly add to es, we add to f all over s squared, we add or subtract ps, we add or subtract q, and here we are going to have cube. That is repeated square on a quadratic function. Let us now get into our first example. Here now we are having our examples whereby we are going to find the Laplace transform of each and every function here. Our Roman one, now we are going to have the inverse Laplace transform of 5s all over 2s squared. We come and add to 18. When you've been given functions like this one, the first thing that we need to understand before doing anything is that we need to understand that the Laplace transform of sine at is equals to a all over s squared. We come and add or subtract. We come and add a squared. The Laplace transform of cos at is equals to s all over s squared. We add to a squared. The Laplace transform of exponential, positive or negative, of at is equals to 1 all over s. We add or subtract a. The Laplace transform of sine hyperbolic at is equals to a all over s squared. We subtract from a squared. And lastly, the Laplace transform of cos hyperbolic at is equals to s all over s squared. We subtract from a squared. These are the basic things that you need to understand. Once you have this concept, you are ready to go. Now let us get into our first example. Here now we are going to factor out 5, because when you check on this side, their Laplace transform, we do not have a coefficient. So we are going to have 5. The inverse Laplace transform of s all over 2s squared, we add to 18. Here we are also having a problem. There is no term on the s domain or the frequency domain that has got its coefficient. To mean that, we must do away with this coefficient here of s. And by doing away with this coefficient, we can factor out 2. And now we are going to have 5 all over 2. The Laplace transform, the inverse Laplace transform now will be s all over s squared. We come and add to 9. Let us now get into our function here. We understand that now we are going to move from the s domain, which is the frequency domain, into the time domain. Here now we are having s. It is the inverse Laplace transform of s all over s squared. We add to 9. Sine, this one we are going to cancel out. According to this question, sine does not have an s on the numerator. This one does not have an s on the numerator, and this one does not have an s on the numerator. So these three are not having s on their numerators. But here, cos has an s, cos hyperbolic has an s. Let us now check on their denominators. On their denominators, we are having s squared plus a squared, and here we are having s squared minus a squared. This one we are going to cancel out. So we are going to use that column, whereby it is going now to be cos at. Let us now get back into our working. We understand it is s all over s squared we add to. Here we must have a squared. And how can we make 3 to be something squared? How can we make 9 to be something squared? We understand that 3 squared is equals to 9. To mean that now 5 all over 2. The inverse Laplace transform here, we are going now to have cos, because we are moving from this side back to this side. We are going to have a is equals to 3 here, t. And now this is going to be our answer. This is how you go about finding the Laplace transform of this function. Let us now get into our example 2. Here now we are going to factor out 3, and we are going to have 3 the inverse Laplace transform of 1 all over 2s we add to 1. When we check at this function, the term s does not have its coefficient, to mean that we can simplify our denominator here by dividing by 2, and that 2 is what we are going to factor out here. So this one will cancel each other, and we are going to have 3 all over 2 the inverse Laplace transform of 1 all over s we add to a half, because when you take these 2 we multiply by this one, we are going to have 2s, and when we multiply by that we are going to have 1. Let us now get into our functions here, and by getting into our function we are going to have 3 all over 2. We are on this side, we want now to move to this side. Let us now check the term that has 1 on its numerator. The numerator, it only means that this term is the one that has got 1 on the numerator. To mean that now we are going to have exponential. We agree that when it is a positive here, we are going to have a negative here. This one I've denoted them wrongly. It's supposed to be a negative or a positive. When we are having a negative here, here we are going to take a positive. And now we are having a positive of a half, to mean that we are going to have a negative of a half t, because that is the term of a. The term of a will be negative a half. And this is now the inverse Laplace transform of our function here. Let us now get into our example 3. Now we are going to find the inverse Laplace transform of 2s all over s squared we add to 4. The first thing that we said, we start with the numerator. We are going to factor out to the inverse Laplace transform of s all over s squared we add to 4. Here now, there is no coefficient here. Everything is very easy, and now we can come and rewrite everything now by checking on our functions here. When we come to this side, we understand that it is going to match s. For the one that, when we come to this side, We start with the numerator. The one that have got s on the numerator are cos at and cos hyperbolic at. But when you check on the denominator, here we are having a positive. So it means we are going to take our function there, and now we are going to have 2 here. And now we are going to have 2 cos our function here squared. Our function here is equals to 4. To mean that when we square 2, it is going to be equals to 4. So here we are going to have 2t. Let us now get into our last function, the Laplace transform, the inverse Laplace transform of 4 all over s squared we add to 9. Here now, on our numerator, we can come and have 4, the inverse Laplace transform of 1 all over s squared we add to 9. Which one has got 1? It is the exponential. But when you check on the denominator, it is x squared we add to 9. To mean that this one is going to be wrong. And what can we do? When this one is wrong, we check on our next function. Cos. Cos has got an s on the numerator. Here we do not have an s on the numerator. This one and this one and this one are all, we cannot use them. Let us now get into our next function. Sine. A. Here we do not have an a. Here we can check on that because it is a positive. But when it comes to this one, this function here, we are having a negative on the denominator. So we are not going to take this function. But now we are going to take this function. Let us now make this function match our function here. And that one means that we are going to rewrite everything here. Now we are going to have for the inverse Laplace transform of 1 all over s squared. We come and add 2. Here we are going to have 3 squared. How are we going to end up now with a on the numerator? Because we must have a here. A here is equals to 3. To mean that we come and introduce 3 here on the denominator and 3 on the numerator. That one means we are going to multiply both the numerator and the denominator by 3. And when we multiply the numerator and the denominator by 3, without changing the meaning of this equation, now we are going to have 4, the Laplace inverse of these 3, we are going to factor it out. 3 all over s squared we add to 3 squared. Whatever we are having here now matches our function here. And we say that once they have matched one another, now we can get the Laplace transform of this function. And now we are going to have our answer as 4 all over 3 sine 3t as now the Laplace transform of, as now the inverse Laplace transform of our function from this point now. The inverse Laplace transform of this function now will be equals to our answer here. And this is how you go about finding the inverse Laplace transform of all these functions. Thank you for your time. Let us now meet in my next session whereby we will be discussing inverse Laplace transform into detail using now the partial fractions.